online.
Okay, so good morning, everybody. So welcome to the third lecture by Eric on the space of holographic CFT. So an important announcement: we had sudden change of we had to change the schedule for next week. So remember, we had an an irregular lecture on Tuesday at 10. Now that irregular lecture is going to be Wednesday at 10:15 a.m. So please keep that in mind. That's even better because there's a strike on Tuesday and not on Wednesday. So that's good. And then there's going to be the usual lecture on Friday morning. Okay. And then the standard announcement. So everything is on the YouTube channel of IPhT. Questions are welcome. When you ask a question, please try to speak clearly because otherwise the microphone will cut you off. Same for the speaker. And then students who need a final certificate of presence. If you're in person, you have to sign this sheet, don't forget. If you're online, you have to put your nickname to contain your surname. And we don't give credit for watching the lecture on YouTube later. And at some moment, there's going to be a 10-minute break. Please be back on time because of the online audience. And after the course, you can have lunch with Eric. So people who don't have IPhT badge for eating, please come to either Ricardo or I will give you some yellow sticker that you can eat with if you follow us to the canteen. Okay, so that being said,
thanks. Great. So this is the third of 5 lectures, and this one will be a little bit more about the toolkit for answering some of the questions that posed in the previous lecture. Next time, we're going to use these tools to bootstrap the space holographic CFTs, as it were. And yet, I don't want to have 2 hours of tools. So, and some of these tools, I think some of you are well familiar with. So I'm going to try to find the middle ground where we introduce some techniques, but don't go all the way into the depths of 4-point functions and the many things you can say about them. With that said, as Monica emphasized, questions are always welcome. So if you want to know some more details, please ask. Okay, so very nice. Good. So we're going to talk a little bit about CFT 4-point functions. I'll introduce some of what makes these 4-point functions. The point being ultimately to then transition into how you compute 4-point functions holographically in a CFT. It's the subject of, as long a history as the correspondence itself. One of the first things that people started doing after the CFT-TV papers was to compute higher point functions. The 2-point function basically just follows once you get your head on straight with the dictionary. But then for computing 3 and especially 4-point functions, you need to work a bit harder. People took a few years to do this after CFT was invented. And then in the years since then, there have been a few different phases, different techniques, different bases introduced, which manifest some of the fundamental properties of holographic correlators that are special compared to generic CFT correlators. And so we're going to introduce some of the basics and then go into the bulk, explain how you might compute some of these and what they tell us about the spectrum of these theories. And then in the end of this lecture, talk about ways to compute large N CFT correlators without explicitly computing Venn diagrams from a kind of bootstrap point of view. And that'll continue next time. So in particular, today we'll talk about well, you might say there's 2 ways to use bootstrap methods to compute holographic correlators. One is top-down, if you're interested in computing, say, n equals 4 superangles or some theory that you know as a string dual. Then you can use the symmetries to your advantage to write down the answers without actually adding up all the Venn diagrams. And then there are bottom-up methods, which just use the structure of the 1/n expansion and the kinematic structure of conformal blocks to make universal statements about spectra of strongly coupled large N theories. That'll be for next time. Today we'll talk a little bit about the top-down aspects after introducing the diagrams, which in the end you can sometimes just eschew completely. Okay. So that's a little bit of an overview of today. So suppose you want to compute a 4-point function of identical local operators O, situated at 4 different positions in RD. You probably all know. We can write this in terms of some overall, what I'll call leg factor, times some function A of cross ratios, conformal cross ratios, Z and Z bar. So sometimes we can use letters U and V. V, and what's the relation? Well, U is V Z bar, and V is 1 minus V, 1 minus bar. And in terms of x1, 2, x3, 4, and so on, I won't write the definitions, but they're just these conformally invariant ratios of differences of distances squared. So what this means is that you can use conformal symmetry to fix 3 of the points, and then the 4th you can think of as being parameterized by these coordinates Z and Z bar in the complex Z plane. So in the simple setting, on the so-called Euclidean section, Z bar is just the complex conjugate of Z. More generally, you can take Z and Z bar to be independent complex variables, and a lot of interesting physics follows from this. Doing this carefully, understanding the physical consequences of this within the subject of many works dating back 10 plus years, and then maybe culminating, let's say, in the reference I mentioned a couple lectures ago by Slava Jashin and Peter Kravchuk about ways in which you can rigorously relate Euclidean and Lorentzian correlators and what does and doesn't follow from certain axioms doing so. I realize now there's something I want to say at the very beginning, which is that last time I promised a document with references annotated. You have not received this document. I have some homework. After lunch today, I'm going to finalize this document, and Ricardo will send it. And in this document, there will be some references that are especially useful to, I'll say, today and the other. So sorry about that. Good. So now we want to use the OPE to expand this function A in conformal partial waves or conformal blocks. So let me draw this in pictures, then we'll write some formulas. So there are different choices of how to use the OPE. Crossing symmetry relates them. We all know that. For now, we'll present a couple of the channels. So in the S channel is the channel for me where U goes to 0. This is where x1 approaches x2. Likewise for x3 and x4. We can write the function A bar as a sum over some intermediate operators phi using the conventional way of drawing these things. And at these vertices here sit the important dynamical data, the OPE coefficients, which couple the intermediate operator to the externals. In the T channel, which is the V to 0 region, we can instead expand generically some other basis. And I've written these as identical primaries. It kind of, in the end, doesn't really matter. If they're not identical, then these two bases of operators will be different in general because of the fact that 1, 2 might couple to something that 1, 4 doesn't couple to. again, I'm assuming a little bit of familiarity with this. If you want me to stop and slow down, please do that. So here, we instead have other OPE coefficients. C1, 4, 5 prime, C2, 3, 5 prime. There's also a U-channel expansion, a lot like these. So we can use conformal representation theory to package these exchanges into conformal multiplets, and the contributions of all of the conformal descendants of the primary are determined by conformal symmetry. So we use the symmetry as much as we can, and we write this instead with sum over conformal primaries, where now this pictorial object would represent a conformal partial wave or conformal block, which are basically the same thing. Up to things that won't really matter so much for this lecture. So introduce conformal blocks, conformal partial waves. So this might be called this block partial wave. And so now we regard these as sums over primaries. I would draw the same picture, just now sum over a primary. And this thing as a function is now different. It sums up an infinite set of contributions. Right, this is a function of cross ratios. In this picture, where these are sums over all intermediate states, this would just be some power. When you sum over an entire conformal multiplet, you're summing an infinite set of powers of cross ratios with different coefficients linked by conformal symmetry. And so you get some function of cross ratio z and z bar. That's the conformal block. It turns out that in even dimensions, they have totally explicit expressions. In any dimension, they have not closed form, but extremely efficient and closed form as sums or integral expressions. Turn out to be very nice objects, as you might expect, because they're determined by a powerful symmetry. I guess take the S-channel expansion, write this as a sum. I'm just drawing the same picture, but now let's emphasize that this is sum over primaries phi, and this thing is the conformal block. So you can think of the conformal block or the conformal partial wave as just the insertion of a projector onto a conformal multiplet inside this 4-point function. So sometimes the block is referred to as G with some subscript delta and L. So this is a function of z bar. These are the dimension and spin of the intermediate operator. And there's some dependence on external dimensions generically. You might see written like that. I'll kind of suppress this notation today. And the wave, you might see written with a W. There are many notations that get used. What's the relation between them? Well, conformal partial wave is just basically a like factor, the analog of this thing, which depends on the x's independently, times the block, which just depends on the cross ratios. Okay. So this conformal partial wave you can think of as inserting a projector here onto a conformal multiplet, but it's just equal to a block times this like factor. And by now I've definitely spent too much time explaining this small distinction, which is really not so relevant. Now, let's say a little bit about conformal blocks. So let me give you a flavor of what these look like by quoting the series expansion for the scalar conformal block, that is the intermediate scalar exchange. This was written down by Dolan and Osborne. The Dolan-Osborne sequence of papers from the early 2000s is legendary. Expressions for conformal partial waves go back really, to the 70s, works by Ferrara et al. These are some standard references. In terms of U and G, the spin takes the following form. Double sum. Okay. So it's an infinite double sum over some n involving Pockhammers and the spacetime dimension D appearing only here. A nice expression. Now, D even, there are closed form expressions. In other words, the sum can be performed. For example, in 2 dimensions, we can write this as a product of 2f1 hypergeometric functions. Very nice. And that's true for any spin L, in fact. Okay, so as you might expect, because in 2 dimensions, things at the level of individual conformal blocks, things holomorphically factorized into left and right, and so spin is just about the difference between the two. So from the point of view of a holomorphic half, it doesn't know about what the spin is, so it's a closed form expression for all spins.
Can you say that the Pockhammer symbols that simplify the dimensions? I mean, it's obvious from that expression that you get hypergeometric.
Yeah, so let's imagine taking d equals 2, then this becomes a delta sub m, and okay, then there's some nice cancellations that happen. It's not, obvious in 1 second, but I think it's obvious in 1 minute, maybe. Okay.
And it's really d equals 2, which makes a difference. I guess if it's odd, it's going to be very the never simplify.
Exactly. You can see here the odd even difference. D is the nicest case, but even in d equals 4, well, what happens is that so d equals 2, it's a product of 2 2f1s. D equals 4, it's basically also a product of 2 2f1s, just slightly decorated. Yeah. Okay. Let's write this properly. Using a kind of standard notation, bootstrap world. This k is just a 2f1 with certain special arguments. So in the case where all the external operators are identical, in particular, these things go away. So it's just beta over 2, beta over 2, beta x. So this is probably familiar to some of you. And at d equals 4, it's similar. Now, in all dimensions, besides this series expansion, there are many efficient methods. So there's the series for the scalar case, but even for spin, everything that I'm saying here really applies for all internal spins. There are integral representations, there are recursion relations, and perhaps most physically, there are differential equations, so-called conformal Casimir equations, of which the conformal partial waves are solutions. So there are many ways in which to approach these. You can expand them to any desired order and cross ratios in whatever dimension you want. Some of these methods are better than that, and there are specific choices of coordinates which also rapidly increase the convergence of this expansion. There's much more I can say. Maybe I'll just stop here. And emphasize that with this data by your side, you can very efficiently compute 4-point functions and try to solve crossing. So what is crossing? This is the associativity of the OPE. So pictorially, this, and likewise for the U channel. And so if we expand in either channel, we equate these expressions, the data appearing on both sides, typically for different external operators, is different. And even when it's not different, it's still a non-trivial equation. And why is it non-trivial? So the conformal blocks are not crossing symmetric. Only the full sum is symmetric. So you use conformal symmetry as much as you can in writing the 4-point function, but that's still not enough to guarantee crossing symmetry. Any questions?
Yes, for my computer. The conformal block is sum over all the primaries, or does the dimension of the primary or factor?
The conformal block is a single, is the sum over a single conformal multiplet. So the primary and all of its conformal descent.
The dimension of the primary enters where in this? The dimension of the
This delta is the dimension of the internal primary operator.
of the pi.
This is delta.
I see. And what's the dimension of O1?
Yes, those appear in general. Here I specialize to the identical case.
Ah, it's an identical. Okay.
In this case, but generalizations exist. Excuse me, I was not totally clear about that. Yes, yes. Let's see. Yeah, surely there's. Physically, why is this the case? He's asking, do the blocks depend only on the differences between external dimensions? Delta 1 minus delta 2. Yeah. So if I mark these with 1, 2, 3, and 4,
Okay.
does the conformal block depend independently on the dimensions or just on the differences? The answer is that it depends just on the differences. And this is something you can see at the level of the Casimir equation. But I'm struggling to get a solid bullseye explanation for why this is true.
In the words, you take conformal block for certain delta 1, delta 2, and then you just multiply it by the conformally varied function, which just depends on x1 and x2. Then it again gives you something conformally varied. You can raise the dimension by multiplying one conformal block by 1 over x1 minus x2 power. To the extent that conformal block is a conformally invariant quantity, which is gets the right limits. You can agree.
Yeah. Okay. Yep. Okay. Well, maybe we can think more about this. Yeah. Any other questions? Now, this is not a bootstrap course per se. There have been many beautiful such courses. With a little more time at this point, I might explain some of the things that the conformal bootstrap not at large N has accomplished in this big picture point of view, but some of them will come up in due course. So now we want to think about correlation functions of large n with an eye toward holographic CFTs, which have large n and strong coupling. And so let us take this function a, b bar, for some 4-point function of operators O, which make it identical in a lot of the pictures and formulas, and expand this in 1 over c. That is 1 over n. It's the same. So we use central charge as our sort of agnostic expansion parameter. Right? So I've written the first 3 terms in this expansion. The first term is the term that you get at infinite central charge. So this is what you might call the disconnected piece. This here, the first non-trivial contribution to the connected correlator, is the planar 4-point function connected. And this 1 over c squared correction is the first non-planar contribution to the 4-point function. And the expansion, of course, will go as not. So the fact that the expansions in integer powers of 1 over c is something that you can see explicitly from the large C counting of 2 and 3-point functions. And so how does one actually go about computing these in the holographic context? Next. Maybe a CFT. Traditionally, one would be summing up Witten diagram. Now, in that context, we can draw a picture, one type of picture for each of these types of terms. So here's our ADS. We have our 4 boundary points, and we're going to be drawing Witten diagrams. What's a Witten diagram? It's just a Feynman diagram in ADS with ADS boundary conditions for each of the bulk fields dual to the local operators in the boundary. And so the disconnected piece at infinite central charge is just the set of disconnected diagrams in the bulk.
The problem function is for light operators or for...
Yeah, so, right, good, thanks.
How do you know you have something?
Assume O is light in the sense that delta O is finite at large C. So
And what you say might apply to heavy light also? Or
what I'm saying so far would apply to heavy light, but it's more non-trivial that this is true. In the sense that when you have a correlator where some of the operators become heavy, dimension scaling with C, then the planar combinatorics don't a priori apply. But if you think from the ADS point of view, now it's like you're computing a 2-point function in a heavy background, and if you think the bulk would have a genus expansion, then the 1 over C expansion of the boundary correlator should proceed likewise. But just from the strict traditional large N CFT point of view, it's true. If the operators become heavy, then the like structure doesn't follow. So calling this a disconnected contribution is really invoking some kind of bulk language. Holographically, at an infinite central charge, G Newton goes to 0. We're imagining all interactions are shutting off, and so all you have is just free propagation. Now, there also would be do this. The cross-channel propagations. I'm not going to draw this. this one, and then U-terminal as well. Now for the planar, well, now you're going to start to see the effect of bulk interactions. So you're going to have diagrams like this, changes, and contact diagrams, but tree-level diagrams. Okay, so these are tree-level diagrams. For these, so let's now you have a non-planar contribution on the boundary. What is this in the bulk? Well, now you just go to higher order in the bulk loop expansion. So now you're going to get loop diagram contributions to a bulk 4-point function. Like this, plus all the crossed. And on and on.
Later, but they correspond to later Feynman diagrams involved. Okay.
No.
Maybe I shouldn't pay attention to what happens about terminology.
Inside the loop, you have when you wrote the loop, singlet which goes inside the loop.
Sorry, say again.
Particles which goes inside the loop, it's singlet.
The single traits.
Yeah. So it should be separated by 1 over t squared.
Yeah, I mean, right. So when you count the suppression by the G Newton at these interaction vertices and the count the propagators accordingly, you're reproducing this overall suppression factor. But yeah, I don't think it's true that sort of diagrams to all of us in 1 over C expansion are always planar when viewed as ADS.
What about headfall?
Those would end up being some kind of normalization of delta on the boundary for the external operator, or these types of effects that would contribute to renormalized quantities on the CFT side. Here I'm say, in a simple case where we assume that O is light and say protected, then a lot of diagrams like that just don't contribute. But yes, in general, you will have, so even if O is light, in some protection mechanism, then the dimension delta O will have some delta infinity plus 1 over C. Right. So you have to account for these, and those kinds of tadpole diagrams will give you these types of terms, but then you soak them up, and then you look for the truly new loop level contributions that are giving different kinds of functional forms to the 4-point function. I can't speak to this word. But those effects are there.
If I understand correctly, well, the dependency in the ADS is just the Newton constant. And so your vertices are proportional to G or something like that?
Good question. So we'll talk more about this next time, actually. I'm performing a slight of hand here. If we imagine something like the graviton propagating, then yes, that is always controlled by G Newton. But for other fields, or for quartic vertices like this, there is no first principles derivation in general that all such vertices must have a G Newton in front. This is this question of whether you can have like a strongly coupled bulk sector where the interactions are not suppressed by the gravitational coupling, but by some independent scale. There's been a lot of work on this in the past couple of years, and often the conclusion is that actually there is a G Newton suppression. So for example, a quartic vertex with a sufficient number of derivatives dressing this interaction actually has to have a bounded coefficient, and so one ends up getting to write it like this. However, or a pure like 5 to the 4th interaction, we don't really have much analytic control over the size of that. There are no strong bounds on that coefficient. So there could be a case, as far as we know, where you have a 5 to the 4th bulk interaction, which gives a contribution to a boundary correlator, which is not 1 over C suppressed. It should be suppressed by some lambda, whatever lambda is. This is viewed as slightly pathological and certainly outside of the typical, canonical computation of holographic correlators. But it is true when I write this, I'm assuming some kind of universality, which tends to be borne out in what we know, and in all top-down examples is always, so far, true. Okay. So we could. So how do you compute these? I mean, they almost compute themselves. These are just Feynman diagrams in ADS. So you need to know the propagators and the structure of vertices in your Lagrangian, and then you write that thing down and try to compute it. So the propagators are simple enough. They end up being hypergeometric functions. And let me just write an example of what one of these looks like if you just try to do it the brute force way. So let me use a color here, let's say green, to emphasize one important point about that, which is that you have all these vertices, okay? In order to make an object which is conformally covariant, these bulk vertices are integrated over all of ADS. So you take your propagators and your interactions, you write down, you stitch them together, and then you have some ADS integrals to do. So this is slightly, different than the flat-space Feynman diagram computation. So these end up being integral expressions, where the integrands often are relatively simple, but end up getting pretty complicated, like once you get out to here. And so just as an historical note, the early works in the CFT were computing tree-level correlators. There basically was no computation of one-loop diagrams until 2010 or so, a paper by João Penedones. And then 6 years later, there was like a more bootstrap-inspired way of computing these things, which gets around the fact that these are hard integrals to do. Quartic integrals over ADS spacetime with hypergeometric functions in the integrand. You can avoid that by thinking about the problem differently. Hopefully, we'll see that by the end of today.
Do they have gravitons running in the loop or just scalars?
Even just for scalars, it's hard to. Yeah.
Has anybody done for gravitons?
Yes, in the sense that you can use a bootstrap approach to write the answer down. Yeah. So. Just to give a flavor, the bulk-to-bulk propagator, what you would need, say, to compute this, or scalar phi, write this BBB, bulk-to-bulk, propagating from one bulk point y to another y prime. And if the scalar has dual dimension delta, and this is equal to e to the minus delta sigma prime times 2 f1 delta d over 2 delta plus 1 minus d over 2 e to the minus 2 sigma prime. Sigma is the geodesic distance, and d, little d, is the boundary. So here also in this formula, you can see that even dimensions simplify. If you take d equals 2, say, these two arguments cancel, and you get a much simpler rational function of e to the minus sigma, or powers of e to the minus sigma, and that's true in all even d. This is the bulk-to-bulk propagator, so the relation to the conformal block simplification in even d is not totally clear, but it turns out that these are essentially the same thing. which is something we learned in 2015 when we realized how to write a conformal block in the boundary in terms of some bulk object called a geodesic Witten diagram. This is just a side comment. These are essentially the same simplifications that are happening on both sides. So, as an example, if you wanted to compute this free-level exchange diagram, where I'm taking everything to be a scalar for simplicity, then this thing, if we call this y and this y prime, is a double space-time integral where we just stitch together the propagators. There's a bulk to boundary propagator, which can be obtained as a limit of this. I've written it down. Let's call that G bulk boundary. So you have G bulk boundary, let's say, just in some sort of schematic notation, from point 1 to point y. And then likewise, G bulk boundary from 2 to y. Then you have your G bulk bulk, y to y prime. And then you have your G bulk boundary from prime to 3. And then finally, G bulk boundary from 4 to y prime. So easy enough to write down the integrand. Doing the integral is another story. So let's actually spend a little more time talking about the disconnected piece.
Can I ask a question?
Please.
So in the limit when I have, I don't know, point 1 and 2 approaching, point 3, 4 approaching, then, clearly I get the biggest contribution from this thing from one of the diagrams. Can I identify the Witten diagram with the conformal blocks, or is that, one propagator with the conformal block, is that,
Yeah, so
the way to get the relationship between?
good. So let me say a little about how you manifest the relation between that diagram and the sum over blocks. I think that's a good question. Yeah. So there's something called a geodesic Witten diagram, which is the bulk dual of a single block. This is similar to an ordinary exchange diagram, except you only integrate these points along the geodesic connecting their respective boundary points. Once you know this, then it turns out that by some relatively simple manipulations of propagators, if you look at this exchange diagram, so the full exchange diagram, you can decompose it into sums over these without too much trouble and without ever having to do any of the integrals. So write it over some prime. You can basically write this as a sum over geodesic Witten diagrams. It's an exchange phi prime. And so once you have this expression, you can the relations very manifest, and you can use the symmetries, and you can see which are the terms which dominate. So indeed, in the boundary sides, you take these points close, and the u goes to 0 limit. The leading term is the identity, and then that's just you map the problems onto each other. You don't need to think about the bulk anymore. And why is that? In case this was from the boundary point of view, the block. So as u goes to 0, the block goes like u to be delta minus L for 2. This is the internal. So when this is 0, that's 1. But for all non-zero twist operators, this is suppressed by some. Okay. So we want to talk a little bit more about the free propagation case because it connects onto this idea of generalized free fields that we talked about last time. It's already kind of manifest, right? As explained last time, generalized free field means an operator, so an infinite central charge CFT operator, which is dual in the bulk to some field, which enjoys free propagation. So at the level of 4-point functions, the generalized free field correlator is just this plus its crossings. Okay. That's what the disconnected diagrams in ADS are computing for you. GFF 4-point function. Okay. So this thing, 1 for the S channel, plus this for the T channel, which is just 1 over x14 to the 2 delta, x23 to the 2 delta, just with the leg factor stripped off, written in terms of cross ratios, and then plus the bar to the delta. So this is the same. It's just this plus this plus. Okay. 1 to 1. Now, written like this, it's manifestly crossing symmetric, but now we decompose it into a fixed channel, and we get to extract the generalized free field OPE data. In this 4-point function, what are the operators that are propagating in a given channel in the intermediate channel? Well, we write this in the S channel, Z and Z bar going to 0. In terms of these sort of pictorial conformal block, we have the identity, that's here. It's a small z and z bar. Which term wins? It's this. And then what's next? Well, it's just 2 times zz bar to the delta. Okay, and what is that? That's the dimension of the lightest double trace composite of the external. Zz bar to the 2 delta is delta plus delta. So that's the dimension of a composite of 2 of the external operators O, each of which had dimension delta. So the full sum is actually a sum over these 2 indices, n and L, we introduced last time. Sum over n is from 0 to infinity. Sum over spins L is over even spins L. Here I'm assuming this is some real field. And there's some OP coefficient, A, n, comma, L, 0. There's an OP coefficient squared times the conformal block for these operators O, O, n, comma, L, which I remind you is basically this with traces subtracted and derivatives acting in both directions such that this is a primary field. This is the full answer. So the decomposition of the generalized free field 4-point function is just the identity plus the sum over these double trace operators. And this thing here is the squared OP coefficient, C O O, O O L. So what is this? It's a thing which you can write down again in terms of Pockhammers. I won't write it, but it's totally explicitly known in any dimension for any of these quantum numbers n and L, and for any dimension delta O. Okay. Good. So these are the double trace operators. It's useful to what do I want to say? Yeah, it's useful to understand this result from a physical point of view. You might have expected that double trace operators appear in the CFT decomposition of this object by way of a kind of cutting mnemonic for this diagram. So if we look at this, and you imagine, okay, we're decomposing it in the S channel. So we would want to cut this way. What do you hit? You hit the identity, that is nothing. This is just the one term. Now if we were to sort of cut, imagine cutting this diagram. This line crosses the 2 propagators. That is the bulk manifestation of the fact that this is a sum over the double trace operators here. So you might ask, why don't you get triple or quadruple trace operators appearing in this decomposition? Well, from this kind of physical cutting point of view, you can't make a cut across these 4 lines without doing something crazy, which is not what it means to make a cut in this context. So physically, this is, I think, a useful picture. It also will be useful when you think about connected tree-level diagrams and loop diagrams. Just like preview, if you take this and you cut it like that, well, you're integrating these points over the full bulk. So equivalently, you can cut this anywhere. And indeed, the conformal block decomposition of this diagram involves the exchange of the operator dual to this, which is a single trace operator, and then sums over the double traces made of the external operator. So just as a mnemonic to understand what the decomposition is of bulk diagrams, this works. This has been developed in a rigorous way, even at loop level, in the past few years. When you do this geodesic Witten diagram composition, that also is totally manifest. Okay, so to summarize, at infinite central charge, the 4-point function of some like single trace operator in the CFT is a generalized free field 4-point function, which is just the sum over disconnected bulk diagrams. And the conformal block decomposition of that explicit, very simple answer lands you on the identity plus sum over these double trace composites, the specific OP coefficient. So this is the story at the 0, the free level in the bulk. And so now, in order 1 over C, this gets corrected in 2 ways. Now there are new exchanges, not just identity, but single trace operator exchanges from the boundary point of view. In other words, these are bulk fields giving rise to exchange diagrams, and what's propagating here? It's just some bulk field. That bulk field is dual to a boundary single trace operator. So there are now single trace exchanges which appear at this level, and their OP coefficients are suppressed by the appropriate power of 1 over C. In particular, large C factorization tells you that this OO phi OP coefficient goes like 1 over root C. So in an exchange diagram, that gets squared and gives a 1 over C contribution. So this operator is appearing anew for the first time at this order of expansion. And on top of that, the data for these double trace exchanges gets corrected away from its generalized free field value. This gives rise, for example, to the anomalous dimensions for these, which we talked about last time. So if we define some A n comma L as over there, COO n comma L squared, and if we define an anomalous dimension, gamma n L, then these two quantities both have 1 over C expansions, which proceed like so. A n L starts with its generalized free field value. Then there's the tree-level correction. Okay. And the anomalous dimension itself starts at order 1 over C. So let's write this as gamma 1, where the 1 over C squared and beyond appear in this ellipsis here. This quantity here is this binding energy from bulk interactions for this 2-particle state, just to call back to last time. This is the equation. And the anomalous dimensions in particular are of physical interest, but also sort of easy to extract from a given expression. Why is that? They come with logs in the conformal block expansion. So why is that? That's because, right, the conformal block, for example, started like u to the dimension minus spin over 2 in the small u expansion. When you have an anomalous dimension for delta, and you expand to first order, this brings down a log u. So that log u is not part of the structure of a conformal block non-perturbatively, but if you're expanding in some small parameter, the coefficients of the logs encode the anomalous dimensions. So if you're just interested, say, in extracting the anomalous dimension of one of these double trace operators from some bulk computation, then you're trying to extract the logarithmic part from the cross ratio. This coefficient will be giving you this type of term. Any questions? Yeah.
When you do these OP expansions, there are also contact terms which are not given by the CFT data. What is the status of those from the holographic side?
Everything in the bulk maps to some CFT data, but you might say those are independent pieces of data which are not fixed by the single trace exchanges. Is that what you mean?
I mean, for the contact terms, for example, there are contact terms which are not in the CFT data. By CFT data, I mean the dimensions of the primary and the OP coefficients, and the contact terms are not included.
I'm not sure what you mean. Whenever we have a bulk diagram, even a contact term, this will contribute to some CFT data. For the case of the difference is, okay, so let me say this a little more clear. This actually is about to be my next topic. I'll spend 5 minutes or so, and then I'll take a break. So I'm going to answer your question now. I think I'm going to answer your question and tell me if I'm not. So there are two types of tree-level diagrams. The first are, let's say, the contact diagrams. Okay. We want to understand what in the conformal block decomposition, what types of operators do these diagrams have support on? As before, we could write down the explicit expression in terms of propagators. I'm not going to because I think the general point was already conveyed. I'll just say in the case where these dimensions, so suppose we have divided the force vertex in the bulk. In the case where these external dimensions are generic, this thing has a name. We'll call d function, which is defined this way: an integral over ADS of the gluing of 4 bulk-to-bulk propagators. When the dimensions are integer, more or less, this integral can be done and re-expressed in terms of other nice functions. So, for example, when the external operators have dimension 1, you can write this in terms of logs and dilogs. When they have dimension 2, just some derivatives of that dimension 1 expression, which give you other logs and dilogs and so on. Now, in the conformal block decomposition, aka in extracting the CFT data, what kinds of data do you get? Well, here we explain the kinds of things that can happen at 1 over C. But because this is a contact diagram, there's no single trace exchange in the boundary associated to this diagram. It just corrects the double trace data. And again, this cutting mnemonic helps you see that. You're crossing 2 lines. You're going to get if you expand in this channel, you'll get double traces of 1, 2, and 3, 4. And you get to read off the corrections to those OP coefficients. So, double trace only. So in the S channel, my conventions is that way. You're going to get O1, O2, and O3, O4 exchanges. In the T-channel, my dimensions is that way. We're going to get O1, O4, and O2, O3. For every such contact diagram, whether it's dressed with derivatives and so on, this is the picture. Just the data itself will change. So to your question, every time you have such an interaction, it will feed into the CFT data. But there's not a single trace exchange, but the double trace data sees and feels this. Is that clarify things?
Yeah, but I mean, what I was saying is that when you take two collision limits of two operators in the field theory,
Sorry, which limit?
collision limit, like when x goes to y, so there can be operator contact terms which goes as delta functions.
Oh, sorry, contact terms in the boundary positions.
Yeah, which goes as delta functions, which are
Sure.
those data are not included in the CFT.
Not included in a CFT.
Okay. So let's say if I take two operators O of x and O of y, there will be contact terms which goes as delta of x minus y.
And your statement is?
And so say with some coefficient, with some c times delta times x minus y, and some so that, and then you have to multiply operators so that the dimensions work out. So those c, how to get those c from the bulk?
I'm not sure what your claim is on the CFT side. You're saying they are there or they're not?
They are there in the CFT side, but
you don't compute those diagrams, you just don't get the wrong result. Whatever you can compute somehow should contribute to the CFT result, otherwise you won't find an agreement. If you just omit those diagrams, you won't get the CFT result, you will get some mess. It contributes in some way.
Are you talking about contact terms in the OP?
yeah, that's because you have constantly separated points. Yeah. Yeah.
By P, the operators are never top of each other, they're separated. If it's separated, the delta function goes to 0. So what do you mean by delta function? Talking about correlation function for the Pelopini terms, what was delta function?
When there's anomaly, when there's anomaly.
But are we talking about correlation function or OP?
Yeah.
You might have correlation function proportional to delta function, but not OP.
Sorry, then I said that.
Is this a correlation?
Okay. It's like when you have, let's say, J and J. So in two-dimensional CFTs, if I take the holomorphic operator and an anti-holomorphic counterpart, we know that the two-point function is 0. But up to contact terms, it's true.
So talk about correlation function, not OP.
Yeah, sorry. Okay, good. That coefficient, I'm talking about that particular coefficient. So how to understand that coefficient from the bulk? If I maybe I'll see, using the wrong words.
I'm not sure I have clarity on this coefficient, but maybe we can talk about it in the break. It's a little bit outside of what we're talking
It's
about.
related to the question which I asked on the previous lectures about the from cell or cells proximity. In some sense, if you're thinking about some symmetry which is closed on cell, then you immediately knock on the term which proportional delta functions, proportional equation of motion, which is similar to what you asked.
All right. Let me ask you more about this at lunch. In the break. Yeah. But just to be clear, there will be no mismatch between the bulk and the boundary. This would be crazy if this were true. So I don't know what the bulk would be responsible for these terms, but things will work right. All right. What did you say?
Is that the professional space or?
I think that's a reasonable logic-based perspective after 25 years of holography.
Experience-based.
It's a scientific evidence-based rational conclusion. All right. So, yeah.
Sorry, before you go on, could you repeat the rationale for the cutting rule of ideas within diagrams, and how from that you can see whether you have double traces or single traces?
Sure. So So first of all, we know that there are cutting rules in flat space. Second of all, this sort of started out as a kind of experimental observation. Works that I'll show you. I missed them a little bit by Fitzpatrick and Kaplan, and then we formalized it in some later work. But the basic point is that you're still talking about, propagation, diagrammatics of propagation of fields in some space, and the fact that it's a curved space doesn't change this locality of the interaction. And so that's some of the feeling of why these are true. It takes a little bit of justification because you can draw diagrams in a funny way and cut them in a funny way and cut through whatever you want. But if you just do sort of the natural normal thing, then you get the right answer. But there's a rigorous statement behind it. But yeah, that I think those are a few reasons why I expect this to be something which is true.
But what does the exact statement? Like if I cut, like for example, in this diagram, we're saying that any cut will just intersect these two lines, and so the intermediate states will be double traces.
Yes.
Okay. While instead for single traces, if you had like the 2, 2, 2 with an intermediate line, there's a cut which intersects a single line, and so it will be single trace. There will be single trace.
Yes.
Okay.
Yes.
So
and this is all so in higher loops and on this continues to work, and it's a manifestation of the unitarity method for ADS. Once you start the perturbative expansion, then you can make the higher loop amplitudes. And then the cutting mechanism, like at loop level, just basically follows from unitarity plus the tree level mechanism. Yes. So again, if we have some exchange diagram, this can be a scalar, maybe it's the graviton. Doesn't much matter what I'm trying to say here. The conformal block decomposition depends on the channel. So in the S channel, we cut this way to ask what's propagating in the intermediate channel. And so we see it depends on where we cut. Equivalently, we integrate over these bulk points. So the lines we cross will depend on which piece of the integral we're talking about. So in the S channel, you do get a single trace exchange of the pi or the metric, or whatever it is, and you get some double tracing. Okay. Whereas in the T channel, these double traces are, again, O1, O2, and O3, O4. In the T channel, though, you don't get a single trace. I've drawn the diagram to emphasize this. And if you were to cut this way, you don't cut through this line. Okay, so I've drawn the diagram to make this manifest, rather than making this some diagonal line that you can imagine cut. But just as a fact of the conformal block decomposition of this object, you just get double traces, the 1, 4, and the 2, 3. Only double traces. 1, 4, and 2, 3. So these are some facts about the CFT decomposition of these diagrams. Let me pause here for the break, and then I'll make some comments about the meaning of this, and then afterwards we'll talk about melon space, and then some of the top-down bootstrap approaches to these, which does not require you to actually compute these position space diagrams explicitly. Question before the break? No? Great.
The break is for how long?
I forgot, 10 minutes.
10 minutes?
10 minutes.
Yeah, there's a timer here, right?
Soft. Remove 10 minutes.
10 minutes.
Let me first ask any questions. Go with this question. I'll make some comments now. The first comment is that the holographic dictionary tells us if we want to compute a 4-point function, we sum Witten diagrams, some order and loop expansion, over all channels. So this means that this is manifestly crossing metric. This is, I think, a magical thing about holography, and I would say we don't fully understand.
It's the diagram of crossing symmetry.
An individual one's not, but if you add them all up, then yes.
Like in field C, detailed diagrams are crossing symmetric, but the object you construct crossing symmetric.
The boundary, we don't compute correlators in a way that's manifestly crossing symmetric.
What we do?
This is interesting.
What do we not understand? The right-hand side of this equation is just reinforcing crossing symmetry by summing over four permutation. So that's crossing symmetric by construction.
Yes.
So then, what exactly we do not really understand?
I would say that in the CFT, we don't compute correlators in a way that's crossing symmetric by construction.
Yeah.
But the fact that we do this in the bulk means that there's an interesting interplay. Things are repackaged in the boundary correlator in terms of these bulk objects in a way that just requires you to manifestly take a crossing symmetric sum of a few simple things.
Take Grisha's comment. Like you said, suppose that we just don't do ADC, we do 5 to the 4th theory and we go to the RG fixed point. And we compute the rectangle perturbation theory. But we'll have the same mystery then. When you do just perturbation theory, you do Feynman diagrams, they are not manifestly crossing symmetric. You go to the RG fixed point, you'll find an RG fixed point 4-point function, and that will be crossing symmetric. But the situation here has nothing to do with ADS, just usual. And it's no more mysterious than it is for 5 to the 4th field position.
Here, the parameter is 1 over C. So I don't know of a way to write a manifestly. The fact that the parameter is 1 over C, which is something which interpolates between families of CFTs, I think is important. It's different from star coupling. And so somehow, when you have a family of correlators and a family of CFTs, when you take this limit, then you get to write it order by order in this way. I mean, even if you're at finite C, I guess it's true, then you would just be computing a crossing symmetric sum of a string having twos. But, yeah, the fact that when you try to write it in CFT language, this is not how we usually write things. I personally think it's interesting.
But how about the thing that you just said? So we just do string theory diagrams, string theory amplitudes. The modular space of string theory amplitudes has certain limits which correspond to different Witten diagrams.
Sorry, that case is actually different. Yeah, right? I know I wrote it. That case is different because when you write your string amplitude, you have your row sheet. You don't
Yeah, those.
sum over the different channels. But here you do.
But it's because you have to integrate over the moduli space of string amplitudes, and the moduli space has several corners which correspond to different channels.
Yes. And somehow this, when you take this limit, or the semi-class limit, it actually looks different. You explicitly sum over these different things which become local bulk Feynman diagrams. So there's something emerging at large C, which doesn't look like what you do for the string amplitude, and it doesn't look like what you do on the CFT side. But let me scale it down slightly. You know, in the CFT, when we compute correlators, conformal covariance is manifest, but crossing is not typically. Here, when you compute things from the bulk, crossing is manifest, but things like, you know, the operator content, not. So it's like you're trading what is the thing that you input and which is the output. But that's so to say in CFT language which operators are propagating, we had to take these diagrams and decompose them.
I have a question. Your starting point was to look for correlation functions of operator whose scaling dimension stays finite with x to 3. I imagine I state for correlation function of operator whose scaling dimension is large, infinitely large. Then formally I could write the same Newton diagram. Then I know that I can say that there will be string modes which will live in the correlation function. At which moment I will run into trouble by just doing this expansion. Somewhere I know the expansion of the diversion. I don't know, it should suffer from some problems. So what kind of problems I will be having if I just follow the diagram?
Well, isn't that the case that we were talking about before? You really have a string amplitude where you have a finite length world sheet in the bulk, then you shouldn't do this. So somehow it's about large C and it's about these types of operators. I would say there's another way in which this perspective is a little bit special.
Suppose that we could say that this expansion will be the variant. Say, imagine I will have expansion which runs on powers 1 on 6 square, but in the numerator it has powers with the scaling dimension standard operator. The expansion will not be right?
Well, it should be meaningful as long as the parameter which is growing is parametrically less than C. Just like, you know, in order 1 over C, you're computing the planar 4-point function. You take large lambda, it's chaotic and there are non-perturbative effects, but it's still in C, it's finite. And no matter what you do with lambda, this is how. So I'd say there's not a divergence in bulk loop expansion. You're still working at tree level. Okay, this is a fun discussion. So let's see, we already talked about this cutting a bit and geodesic Witten diagrams, things I want to mention. Let me make one more comment. So from the part I erased, we talked about contacts and exchanges. Contacts have support on double traces, exchanges have support on single and double traces. The fact that the exchange diagram has support on the double traces too means that some piece of that double trace data is fixed by the single trace data. Why? Because when you have your single trace operator, that means in the bulk there's some diagram like this. There's some vertices here, with OP coefficients, and there's some double trace contribution from this. But this is just fixed by the single trace exchange in the sense that this field, phi, is dual to a single trace operator, where these vertex factors are fixed by the OP coefficients of that single trace. So up to contact diagrams, the single traces fix the double traces. And this is So this fact is actually a nice segue to talk about melon space for a moment, because it becomes totally manifest in melon space. We have to work a little bit in position space to see this. Thematically, it seems but it becomes even more clear in melon space, because there's kind of a way to manifestly separate the single trace and double trace contributions to a given amplitude. So let me introduce melon space. This won't take up too much of our time, but I think it's worth it because I want to bring the treatment holographic correlators more to present day, and these position space methods are slightly old-fashioned. So there is an integral transform, a double melon transform, which allows us to trade our amplitude A as a function of position space cross ratios U and V for a melon amplitude, which is a function of melon variables S and T. Let me write this, and then we'll talk about it. So here I'm writing the amplitude for a correlator of four identical operators. Dimension delta. And define some U hat for delta minus T. Okay. This is the melon amplitude. This thing, M S T. And this is just some measure chosen for a kind of conceptual convenience. Here, these are the cross ratios U and V to certain powers of S and T. So U hat is just this combination. And then there's these squared gamma function factors. We've just done an integral transform. And this was first, well, first in recent-ish times considered by Mack, and then its utility in the holographic context was recognized by Andonis in a solo paper from 2010. So why is it useful? Well, first of all, let me just point out this melon amplitude is manifestly permutation symmetric in ST and U. And as you can anticipate by the choice of notation, here S and T are like Mandelstam S and T for flat space amplitudes, but radius amplitudes. That's the basic idea. And there are two salient points about this expression. The first is that, so if we look at the three-level melon amplitude, right? So the 1 over C piece of this would map into some 1 over C melon amplitude N. There are two types of contributions, contact and exchange diagrams, and they look extremely streamlined in this language. And again, in some parallel with the story with S matrices. The structure for contact and exchange diagrams is as follows. So for an exchange diagram, you have poles at the location of the single trace operator's twist and all of its conformal descendants. Okay, so this gives simple poles like say in the S channel, 1 over S minus some tau star, where this would be the exchange of some operator of twist tau star, plus a bunch of satellite poles with numerators given by these so-called specialized Mach polynomials. Not important for what follows. The point is that you get poles in the melon amplitude M from single trace exchanges. So let me size this. Okay. These are the only poles of M, just from the single trace twist. So in particular, if you look at an exchange diagram, and you ask, what is its Mellon amplitude? The Mellon amplitude itself just has poles from the single trace operator. Where are the double trace contributions from that diagram? They're coming from the poles of this measure factor, these gamma functions. Notice that these themselves have poles when ST or U hat equals 2 delta, which was the twist of the external operator double traces. So there's this kind of decoupling between the single trace data, which is here for an exchange diagram, and the double trace data, which is here. So this makes manifest the second point that for an exchange diagram, the single traces totally determine the double traces. And for contact diagrams, so contact diagrams, T is just some polynomial in S and T, where the degree is fixed by the number of derivatives of the vertex of the contact diagram. So that doesn't introduce any extra poles. The only poles are coming from here, and the coefficients of those poles, which give the actual anomalous dimensions and OP coefficients of those double trace operators, are coming from this evaluated on those poles. So the polynomial appearing here encodes that data, but it doesn't introduce new poles. So the analytic structure, in short, of M strips off the single trace stuff alone, and the double traces are sort of fixed from these poles alone, with this evaluated on its residue. So it's a nice conceptual separation of this fact that double trace data is fixed by single trace up to contact diagrams, and contact diagrams are just these polynomial pieces here. Well, it's a subtraction in the amplitude context.
Where does it follow from once again?
Where does what
Where
follow?
does this property follows from?
So you can think of it as just a fact of this transform. So if you take a Witten diagram of that type and you do this, then this is what you find. But I mean, if you didn't have to, you could define the Mellon amplitude as just this, but it was a good choice to extract these.
And you're saying this holds to any number of loop expansion, not on particular level.
Good, yeah. So this was very helpful for us in doing these first seamless loop calculations, because since you're transforming this into some statement about analyticity and degrees of poles and so on, it became clear that at one loop level, what is happening? This is acquiring poles at double trace locations, which combine with these to make triple poles, which then give you the kinds of contributions to anomalous dimensions that you need at order 1 over c squared. Log squared U terms in particular, if you were to go back to position space. So yeah, the statement at loop level, and the order is that the degree of the poles here at the double trace locations is bounded by the loop order, and to write down the amplitude, you just need to then fix those residues. They are in turn fixed by the orders below, by unitarity, and that's basically what allowed us to avoid using position space. Things can get a bit more complex than that in top-down situations when you have mixing, but the basic story. I'll show these complications. At every order in 1 over c, you will still have polynomial ambiguities. These are like renormalization, finite renormalization scheme ambiguities in terms of expansion. Those will appear as some choice of polynomial. So just to be explicit with one example, I have a 5 to the 4th vertex, so it's a scalar form vertex with no derivatives. The Mellon amplitude is just a constant. If I address this as derivatives, say a d bar to the 4th, then this becomes a second order polynomial that's permutation symmetric and ST and U. the question of whether the contact terms themselves are constrained will be something we talk about. The coefficients in particular are constrained, and whether you can have arbitrary finite sets of contact terms in a given Lagrangian is a question to which the answer is no. We'll talk about that.
Yeah, you mentioned that Smiling amplitude could be considered the scalar amplitude ST and U model star variable. Which series scalar amplitude corresponds to?
Which theory?
I start from correlation functions, so I introduce this object and always scalar amplitude. Which theory?
You want me to say something other than the theory in the bulk, the relevant field contents?
No, in general, is it? It looks like a measure. No, you start from correlation function. So
yeah.
So there is a distinct correspondence which telling you that you're talking about scalar amplitude in bulk.
Yes.
We have this object M, which has all rights to being exactly the scalar amplitude, but it is not.
Well, but it is. I mean, to call this an ADS scattering amplitude is
This is MS is the scalar amplitude of whatever states the move to go efficient way.
Yeah.
Maybe it's a legitimate question to ask in the flat space limit, what is the theory you get out from this particular M?
Yes, so in the flat space limit, which is the limit of large S and T, the null amplitude, yeah, so in Giroir's paper, one of the main points was that this allows you to take the flat space limit in a clearer way, following these older works about that same subject, and that it lands you on a scattering amplitude of the flat space limit of your bulk theory, at least in a certain kinematic regime. This is still an ongoing story, but yeah. So that question is a legitimate question. Of course, the answer is just, so in the string context where we understand things constructively, the answer is the flat space string theory from which your ADS background descended. But yeah, often this technique is useful in reverse, where you might like to fix some quantity in the string theory Lagrangian, and you use large C bootstrap techniques to construct the small amplitude in the ADS theory, and then you take this flat space limit and reconstruct some vertex in the string theory Lagrangian. We'll talk about that next time too. Good. Yeah, thanks for bringing that up. So this is one of the useful things of the Mellon amplitude formalism. Taking the flat space limit is easier.
Okay, so is it then a general statement, or is it not completely clear that the flat space limit of the Mellon amplitude gives a corresponding flat space amplitude?
I'd say
flat space bulk theory.
Yeah, no, this is definitely true at the level of, landing on an object which satisfies all of the kinematic requirements of a scattering amplitude in flat space. The question of whether it corresponds, it is an amplitude in a consistent theory, is a different question, which is really about whether you started with a Mellon amplitude in a consistent ADS. Yeah, but yeah. In Giroir's paper, he demonstrated that taking this limit of the Mellon amplitude, M, lands you on an S matrix with the properties of an S matrix that you want. But still, that statement's been refined over the years, because if you take large S and T, then, well, you talk about how to scale them relative to each other, and if you want to preserve the full S and T dependence of your S matrix, then you need to do this carefully.
Are there some examples where, for a specific top-down construction, they match? I would guess so.
Yes. Yes. So one example is the fourth Mellon amplitude. It's a constant. Flat space limit is a constant, and this would
no, but in an actual type 4 theory, in which bulk theory?
Yeah, so I'm being a little cheeky. If you take the n equals 4, yeah, it's 5, free-level amplitudes in Mellon space and take the flat space limit, then you get back the graviton S matrix, 4-point S matrix. Correct this with all the corrections, then you get back those corrections. The levels which they've been computed. Yeah. So, right. So in particular, yeah, maybe just say a little more about this. I could be a little clearer about the single trace exchange diagram case. But the point is that, I mean, you can, yeah, so if you have some pole in your Mellon amplitude, okay, the residue here, the function t, okay, polynomial t. The fact that this is a shift, right? Even if there are massless fields here, your ADS Mellon amplitudes will involve 1 over s minus some shift. You take a large S limit, this just becomes 1 over s, which is the massless pole, the S matrix pole of the massless exchange. You can think of this as a finite size correction due to the ADS box. So expanding a large S, the leading term is just that, but then you get an infinite series of corrections that resums into this shift. So that's a useful way to think about the form of ADS Mellon amplitudes. Even for massless fields, you get these sort of shifted poles. That's encoding the fact that LADS is finite. Okay.
Good way of going back to the ADS limit. Sorry, there is a good way of going back to ADS. Yes, there would be no algorithm. I think.
Good question. So, short answer, no. I mean, you've lost information, obviously, but still, I think it's a good question in the sense that you'd like to be able to construct, say, a 4-point ADS Mellon amplitude by taking the collection of n-point flat space amplitudes and, say, order by order in a 1 over LADS expansion, reconstructing the ADS amplitude by some kinematic limits of this collection of n-point amplitudes. So what I mean is that this is something that some of the postdocs and I over the years tried to think about, but haven't managed to figure it out. But morally, if you think of the ADS solution as this, it's a background of your flat space theory, say the 10-dimensional string theory, and this is ADS back to this flat solution, or what have you, then this is a non-trivial geometry. So relative to flat space, there's a back reaction, and the gravitons of the 10D theory are generating this coherent background for you. And you'd like to kind of construct this order by order in some sense where you take your 4-point flat space amplitude and order by order, you insert some gravitons into that you're taking some kind of soft limit of. And if you were to sum up this infinite series, then you might hope to recover the 4-point amplitude in the full background. I haven't managed to make this work. This is some kind of vague research project that something like this should be true. Yeah, to put a little more meat on that, if you have some vertex in flat space, like by let's say we have some R to the 6th vertex, or there's some contraction of Ricci tensors. You can, and if you have some solution like 5 times S5, okay, you can put some of these Ricci's on S5, then they will contribute to a lower point amplitude in ADS5. But they'll give you a term which is subleading in the flat space limit at that, at 4 points in ADS. Because it's suppressed by extra derivatives. So the collection of n-point amplitudes in flat space should be enough to reconstruct 4-point or just fixed m-point amplitude in ADS, this would be the reverse version of the question. I think it's an interesting. I hope that made sense. We have a little more than 20 minutes. And so now I just want to talk a bit about some top-down bootstrap approaches. And next time we'll do bottom-up and really see that you can just, by thinking well about the 1/n expansion on the CFT side, avoid bulk diagrammatics almost entirely. But it's an important part of the subject, so that's why we talked about it. So let us go back to this example building on last time of n equals 4 super n moles at strong coupling in order 1/c. So say planar n equals 4, large stiff coupling where it's dual to ADS 5 times S5 supergravity. And we recall that this primary O2, which is in the stress tensor supermultiplet, is dual to a scalar in the bulk, which is part of the ADS5 supergravity field concept. So to compute 4-point functions of O2, we're computing some 4-point amplitude in this ADS5 supergravity. And at planar level, we just need to do it. We can ignore the S5. We just use the consistency to ADS5. And so this was done like in 1999. Once people understood how to compute general correlators, they said, let's look at the type 2B action. We have some specific set of vertices. Let's add up all the diagrams and get an answer. And so for our purposes, we can think of, well, one of the outputs of this, if I write down here, it's a bit low. Yeah. So there were these works by Mathur, Friedman, Matusis, series of very nice papers. And so if we compute 2 4-point function in order 1/c, this is a tree level calculation in the bulk, then the non-trivial piece of data here to extract is this first order anomalous dimension for these two composites. And we talked last time about these plots in that bootstrap paper, Beamer, Stelly, and Ben Rees. And so just to show you, the formula for this, so this is the first order piece. So there's a 1/c in front of this. This is -4, 1, 2, 3, and plus 4 over L plus 1 times L plus 6 plus 2L. So that's the formula for these composite anomalous dimensions. It's very nice. Note that this is negative for all n and L. Note that if you take n to infinity for a fixed spin, this goes like n cubed, which can be related to some properties of the OPE of the 20 prime and the flat space limit. On that next time, I hope. And so we talked about how this bootstrap paper sort of reproduced this. The line that we saw, that slope, was the n equals 0 version of this. Okay. The n equals 0 and L equals 0, 2. But suppose you want to compute the full amplitude. We can diagrammatically you sum up a bunch of stuff, and sure, there are nice cancellations, but it's nice to sort of avoid this if you can. And so this was done in a nice bootstrappy paper by Stelly and Zhao. in 2016 or so. So they computed this thing, right? So C at large lambda, the supergravity limit, without actually computing. So I had a couple of papers. One of the papers is called how to remember the details. There's an old paper by Friedman and friends called How to Compute Holographic Correlators Without Even Trying. No, How to Succeed in Z integrals Without Even Trying. Z integrals are the integrals you have to do to compute bulk correlators. How to Succeed at Business Without Even Trying is some old musical, so it was a joke. And then in this recent paper, it's called How to Compute Holographic Correlators Without Even Trying or something. The without even trying is not computing any Witten diagram. The success, I guess, is the fact that they were done. So what did they do? They computed this thing by imposing some consistency conditions physically motivated by the problem of interest. And they worked in Mellon space, which was important because it just simplifies the analytic structure of the thing tremendously. So they're computing this three-level amplitude for 2222 Mellon space. What did they impose? First, they impose crossing. That's kind of for free in Mellon, but that's why it's good. So they want some totally permutation symmetric function of ST and U, or what I called U hat before. They impose the superconformal word identities on this correlator that come from n equals 4 superconformal symmetry. This amounts to the statement that this can be written as some sort of piece of the function which comes for free, which actually corresponds to the free limit of the correlator, plus some piece which is the dynamical or interacting piece, and processing n equals 4 supersymmetry accordingly leads you to have to only compute this relatively simpler function. So far this is just symmetries. Now comes some dynamical information. So they say, we know that at strong coupling in this theory, the single trace spectrum becomes extremely simple. All of the long operators decouple, such that in this 2-2 OPE, all that appears is the identity and composites, and 2 itself. Okay. So this thing is the statement that if you look at this O2 times O2 at infinite drift coupling, you get the identity plus 2 itself plus multi-trace operators. This is very useful in the Mellon formalism. Remember that up to some possible contact ambiguities in M, all you need to write are the single trace exchanges. Right? The Mellon amplitude itself just encodes the single trace exchanges. Here you just have one, and so there's not some whole tower of stuff you have to include. And you know this piece, the 2-2-2 coupling, those are 3 protected operators. The OP coefficient is fixed and known because they're half BPS. There's a non-renormalization theorem for half BPS 3-point functions in n equals 4 super Yang Mills. So even though you're at large lambda, you know this coefficient. It's lambda independent. And so then you know the identity. That's trivial. You know this piece. And the rest is just multi-traces. But that means you know just about enough to write down your Mellon amplitude at tree level in this regime of large lambda. And finally, and not unrelatedly to the previous point, they impose that in the flat space limit, you land on the appropriate graviton 4-point function. In other words, because you're at strong coupling on the boundary, this is supergravity in the bulk. In the flat space limit, you should get the string amplitude prime is 0 again. You get just a free-level graviton S matrix. Turns out this is enough to guess, to find bootstrap the answer for this code. Am I going to write it? Yes, I'm going to write it, but yeah, that's why I decided to do it here. I'll raise it, I suppose, in a moment. So this requires a little processing to get the exact formula, so I'm not going to write the exact formula because I don't think we need to take our time to do this. When you process these super conformal word identities, there's some stuff that happens, and you trade M for some M tilde, the so-called reduced amplitude. So I'm going to write the formula for that. Okay, so M tilde for this 222 case is up to some normalization. Just this. In position space, if you look at the old expressions from these papers by Doker, Rastelli, Mathur, Matussis, et al., the answer is pretty simple. It's a finite sum of these d functions I mentioned before. But this is better. Okay, this is definitely better. And the flat space limit is manifest. The large S and T you have. This just goes to 1 over STU, which, you know, in the supersymmetric context, stripping off this thing that sits in front of the amplitude is just the
This part is multiplied by 1 over C. This is the 1 over C part.
yes. This is,
Was anything imposed about large S and T or contact terms, or you just say?
no, this is finite S and T. And
No, but I mean, in the rules, there is nothing about behavior at large S and T.
that's actually what this is.
Okay,
yeah.
You have also okay.
They say large S and T, we need to get the right limit, which is large S and T limit of this. So that was used. Yeah. And this is where strong coupling comes in here, because if you're at finite coupling, then there's an infinite set of single trace operators which contribute here. And that would mean that in the flat space limit, you land on Virasoro-Shapiro, not supergroup. Of course, we know that. To actually know that whatever the Shapiro amplitude is in NES5 times S5, if you take the flat space limit, you must recover the flat space actual Virasoro-Shapiro amplitude. But in the strongly coupled regime, it's simpler, and so you can. Now, part of the power of this approach is that you can do better than just looking at 2, 2, 2, 2. You can look at 4-point functions P1, P2, P3, P4, which where P is just the half BPS charge of the operator OP, which we've talked about in past lectures. And so, in fact, there was a conjecture made for these 3-level amplitudes of P1, P2, P3, P4. In bulk language, these are arbitrary KK modes on the 5-sphere. And so we look at M tilde, 1, 2, 3, 4, P, C, large lambda. There's some formula for this, which I perhaps should have copied so I could write it down, but it involves some sum. This was first made as an ansatz, I guess, by Rastelli and Zhao. I mean, this also was, let's say, guessed or inferred from the set of bootstrap constraints, not strictly proven. Okay, so there's a formula for this. And this was then proven in a paper by Karen Huo and Trin. Okay. So the upshot is, for arbitrary S5 KK modes, the tree-level supergravity 4-point function is known in a very simple form, which generalizes this to some sum over meromorphic functions. It's a finite sum for some finite set of P's. And it's a very nice story. And the comparison to position space really shines when you look at higher P. What was known in the literature before was the amplitude for some p bounded above by 5 or something. And so you go take p, if you look at the 5555 amplitude or something, this was, again, written as some linear combination of these d functions, but the linear combination is growing, there are more terms, they're getting uglier and uglier, and the computation stopped because they were just getting too hard. But here, now you know them all in a very compact universal way. One of the things that these authors observed as well is that there's some kind of hidden conformal symmetry that governs these amplitudes that descends from 10 dimensions. This is not understood at any conceptual level still, I would say. But what it amounts to is the following sort of moral statement. If you want to compute a 4-point function for any KK mod on S5, well, they all come from the same 10D supergravity fields. So they should all be related in some way. And it turns out there's some kind of 10D conformal symmetry argument that you can use to write down a generating function for all of these amplitudes, which has an enhanced, the generating function itself has an enhanced symmetry, which looks like 10D conformal symmetry for this generating function of amplitudes. And where the symmetry is coming from, why it's governing these things so strongly, is not understood. It's made more as a kind of observation, which then, in some works by Hinek and friends, was used and shown to lead to a really dramatic simplification of the structure of anomalous dimensions for P1, P2 type composites, tree level. So there's something beautiful happening here. And you know, it's not a shock that something beautiful is happening. In the case of N equals 4 Bragg-Mills, it's strong coupling, but the way in which it's happening is very nice, and the Mellon technology was really important for all of this story. This has also been generalized to other spacetimes where you have ADS and sphere factors in a nice combination. It's in conformal symmetry stuff, but a sort of derivation of when this works and why it works is lacking. And I'd emphasize in particular that when you go away from the supergravity limit to the bona fide string theory by turning on alpha prime, this fails. So it's something emergent, and that remains to be understood.
Symmetry works also tree coupling.
Yeah, right.
So
So more than
you're saying it works tree coupling, it works strong coupling, but then what doesn't work?
in between, yeah. So
Does not work?
yes, correct. So I think even in the alpha prime expansion, you see it start to break down. This is clearly found in some papers by Hinek and friends, where they look at the anomalous dimension matrices, and let's put it this way. I mean, you can't correct me if I'm wrong, but there's a kind of universal formula for these in supergravity, which amounts to writing your Mellon variables, writing your momentum on a kind of 10D momentum basis, and then if you want to extract any one of these, you project in a suitable way. You start to include alpha prime corrections that stops giving you the right answer. In other words, the right answer can be computed, like you can say directly, and cannot be massaged into a form where for any p, you can just extract it from a similar generating function in terms of 10D quantum numbers.
How could
So conservatively in alpha prime, it starts there.
the thing is that it's how could it possible that you have symmetry which, and for when you coupling constants are two extreme cases,
Yeah.
the middle breaks.
So just to be clear, so this conformal symmetry works at leading order planar limit, but both at leading order small lambda and leading order large lambda.
So at leading order and large lambda works, and then it stops working. At small lambda, it works beyond just leading order. So like conservatively, in small lambda, there's a paper by Coronado and Karanhuo that shows that it works order by order in the sense that, yeah, you can organize these 4-point functions for arbitrary PI in terms of some Tierney variable.
Is there any knowledge of whether it works at non-planar level, but maybe at leading order in large lambda?
Or in perturbation theory? Well, let's see. So a non-planar level leading order in large lambda, the theory formally has divergence. But if you subtract that and talk about the amplitudes there, there's not enough data to check this against. Yeah, I don't know. Sorry. I don't know. Yeah, Hinek, perhaps you know better.
Yes, it's not exactly clear how the symmetry would manifest itself. There is a piece of the answer which has the symmetry, and then you kind of need to fix it by hand some way. But yeah, it's not fully understood.
It's a weak coupling in the non-planar or the investigated.
Yeah, there I don't know. But maybe I can comment that the manifestation of this symmetry is very different at strong versus weak coupling. Weak coupling perturbation theory, there you see it at the level of the integrand, not at the level of the full amplitude. They are very different, the two mechanisms.
Okay, so I also want to this story. There's also a similar story for the 2-0 theory. The 4-point functions of arbitrary decay modes on S4 can be written in this Mellon space formulation in a nice way by bootstrapping them with the same set of principles. Basically, the same list of consistency conditions where there's no lambda there, but because you're in large C, we know that you're in the supergravity regime. So, M theory. So this is a nice story here as well. And that is what I want to say about this top-down way of bootstrapping these amplitudes. And next time, we'll talk more about how to do this a bit from the bottom up, and then center, let's say, on this HPPS conjecture about the emergence of the bulk and what constitutes a holographic CFT, and then some constraints on ADS effective actions using various kinds of bootstrap consistency conditions that narrow the space of theory considerably. And then that's it. You're welcome.
So about this M being scattering amplitude ideas. So logically, if I have better amplitude, I have to take Fourier and then to go to the residues of. But you're not doing this, you just go to the main space. To me, that's kind of counterintuitive. Normally, if I were to interpret population function scattering amplitude, Fourier residue. But here, you're just writing the formula saying that that's the same, different ways. Is for this.
Well, the prescription is first you go to the Mellon space, and then you take this limit, kinematic limit of large S and T. I mean,
No. I want to go as far as. Okay, I'm saying within ideas. So I have recipe to configure 4-point correlation function. Now I want to say I use a JCFT dictionary to want to interpret this 4-point correlation function and scattering amplitude of certain states in the ideas. That's real scattering amplitude. You're saying that I take Mellon transform, Mellon amplitude will be scattering amplitude with S being on this time only. These are I accept, but I would say the logic way would be just if you have object which depends on 4 coordinates of the boundary. I take Fourier with respect to points. I get a function of numerical variable. Then I go to the LKZ procedure, just going to the residue with respect to corresponding masses. It's different procedure compared just taking the domain. That is why I'm confused. Why is one is equivalent to another?
So I think your question is, if I understand correctly, why? So when we say that the moment is the right analog, why doesn't this smell like the construction? I think there's a better answer to what I'm about to give, but at first, let's say it was kind of when you form this transform with, especially with this particularly chosen measure, then this thing has the properties that you also have in an analogous flat space matrix with the same types of particle exchanges and interactions. But I think what it's telling you is that the momenta are not the right conjugate variables to think about when you want to take the position space correlator and construct. Somehow it's the Mellin variables that are the right ones. And Mellin is sort of conjugate to twist, and maybe that's the right way to think about it. But yeah, I don't have too much more to say, but I think there's a set of papers where I should more closely back to you about how they think about this question. I guess it's sorry, just also point out that if you're away from the ADS setting and you just want to say, can I take an CFT correlator and write it in Mellin space? There was work by Sasha Joao and another Joao. They interpreted Mellin amplitudes, ... They tried to explain for what regimes of parameters, like conformal dimensions of the external operators and so on, this transform is well defined, which Mellin amplitude exists, and whether it's always meromorphic, and so on. The short answer is that there actually are some limits, seemingly, on when, as currently defined, the Mellin amplitude can be said to exist, but I'm not sure that's really something.
Just the construction here looks like it's very tight to the cross ratio, whereas presumably in general you want to have endpoints on the boundary. Variance of them. I mean, is there a way of making this Mellin transform look more like a transformation of the points on the boundary? Yes, set of endpoints on the boundary.
Let's see. Yeah, so actually in the original works it is written that way, but after some processing you can write it just as a transform between the function of cross ratios. So SNT, yeah, so they are related to, so if you start with some 4-point function of x1, x2, x3, x4, then you can define a Mellin transform where you have some Sij's, and after some processing and relabeling for the 4-point case, it amounts to this. So I think that actually doesn't get at this previous question. So.
I was thinking but just in general, then you can do the Mellin transform as a function of endpoints on the boundary.
Yes, you can. Yeah, and that's what they did. I mean, sorry, Joao was the first paper. Then there was a set of follow-up papers, one by several authors with Jared Kaplan and Miguel Palos and Bolt Van Rees and Subrat Raju and Joao. That's it. Yeah, so that's in fact how they do it.
No question? Okay, if there are no more questions, let's thank Eric again. And and students need to sign the things they haven't signed.